Hi goers, welcome to the Chapter 8 review video. Today we're going to be talking about radical chemistry. So the first thing in this chapter that we're going to talk about is bond dissociation enthalpy. And bond dissociation enthalpy is basically just a measure of bond strength, and that also refers to the amount of energy required to homolytically cleave a bond. So the term homolytically cleave means to break a bond where two fragments are generated, and each one of those fragments will retain one of those electrons in that bond. Recall from Gen Chem that each bond has two electrons in it, so if we were to homolytically cleave a bond, this is a situation where one of those fragments that comes off retains one of those electrons, becoming a radical, and the other fragment is also going to retain one of those electrons, also becoming a radical. So the more stable that radical will be, the less energy required to, break that bond, or a lower bond dissociation enthalpy. So let's kind of like relate all of those concepts, because I know it's a lot of terms. So if we were to, homolytically cleave this bond, it's something, oops, let me make that smaller. It's something that looks like this, and we're using half arrows to denote that only one electron is going to each fragment. So we're really generating, in this case, so the amount of energy to do this is referred to as bond dissociation enthalpy. And how much energy is required to do that refers to how stable that radical is going to be on the carbon skeleton. So if we were to homolytically cleave this, the result would be something that looks like that. Same thing over here. And same thing over here. Okay, so this would be the result of homolytically cleaving, all of these bonds that are indicated. And then now we just need to talk about radical stability, okay? So, the first structure over here, this is a secondary benzylic radical. So pretty stable because of the fact that it's close to that benzene where it can potentially resonate. So secondary benzylic, so pretty stable. Over here we have a tertiary benzylic, so that's even more stable than the first molecule. Over here we have a plain secondary, and over here we have a plain primary. Okay, so the more stable that radical is, the less energy required to break that bond, meaning a lower bond dissociation enthalpy. So if I were to say something like 4 equals the highest bond dissociation enthalpy, and number 1 equals the lowest bond dissociation enthalpy, we could rank them as follows. So this one would have the lowest bond dissociation enthalpy because we have a tertiary benzylic radical. Over here we have a secondary benzylic, so that would have the next lowest amount of bond dissociation enthalpy, followed by this one, and followed by this one. Okay, so bond dissociation enthalpy refers to how strong a bond is, refers to how stable that radical is going to be. So we have to make sure that we understand how to relate all of these terms together. Okay, so if I said, which molecule has the strongest carbon-hydrogen bond, it's going to be the structure over here because it's going to take the most bond dissociation enthalpy to break that bond because of how unstable this primary radical is. Okay, so we need to, have all those terms in mind. Okay, so let's move on to our first set of reactions in this chapter. So there was only 3, but the mechanisms are kind of different than what we've used to seeing. So let's pay attention to those. So free radical halogenation, and there's 2 types. There's bromination and chlorination. So what this H nu means is that that's a source of light, and that source of light is capable of homolytically cleaving the bromine-bromine bond or the chlorine-chlorine bond, and this is called initiation. So that light has a higher enough energy or a high enough frequency to homolytically cleave this bond to generate 2 bromine radicals. And likewise over here, we could show these half arrows where we generated 2 chlorine radicals. So, what's the difference between bromination and chlorination? So if we were to look at our periodic table, we can see that bromine has a larger ionic radius than chlorine does. And that's because as we go down the periodic table, we have more and more shells. So, we have this single unpaired electron radical, and, the larger amount of space or the more atomic orbitals that there are there, the better it is at accommodating that extra electron. So since bromine is larger, so if I drew it, properly as such, and chlorine is smaller, we could say that this bromine radical is more stable because there's a lot more space to accommodate that radical than, this chlorine radical, which is less stable. So we know that less stable parallels to more reactive. And we know that more stable parallels to, less reactivity. Okay? So we can also, put this all together saying that the less reactive something is the more regioselective it's going to be. And the higher reactivity is the less regioselective, or the non-regioselective, or non-regiospecific. Okay, so hopefully that rationale or all that logic kind of brings us to this point where bromination is going to be regioselective in forming the more stable product, where chlorination is going to be not regiospecific in the sense that it's going to form a mixture of different products. So let's kind of look at the mechanism to understand, what's going on here. So let me erase and make some more room. Okay, so I'm just going to take this first structure all the way down below. So we had a benzene, okay, and we had this carbon fragment, okay, and I'm going to just draw this hydrogen over here. So each mechanism, or in terms of radical chemistry, no matter what type it is, it's going to follow three distinct steps, and it's initiation, propagation, and termination. Okay, so the first one is initiation. Okay, so initiation is what I showed earlier, where that bromine source is going to be homolytically cleaved by light to form two bromine radicals. And that's it. That's all that there is to initiation. Propagation is typically two steps. That's the next thing, propagation. And that involves that bromine radical coming into contact with that hydrogen and abstracting that proton, forming a radical on the carbon skeleton. So propagation kind of follows something that looks like this. Okay, so I guess I'll just draw this another color. So one of those electrons from that carbon-hydrogen bond is going to meet this bromine radical, and that other electron from that bond is going to stay on to that original carbon skeleton. So the resulting structure would look something like that. Okay, so that's the first step of propagation, but then we have to somehow add that bromine source. So if I were to, take that product from the first step of propagation, okay, and I'm going to take another source of bromine. Now that radical is going to react with the bromine to add the bromine onto the carbon skeleton, and then generate another bromine radical. So we just added bromine to the most substituted position, and the reason why we chose that position was because, remember, the bond dissociation enthalpy for that carbon-hydrogen bond is relatively small because of how stable that radical is. So we chose that proton specifically, and then don't forget that we generated that extra bromine radical. Okay, that's important because this extra bromine radical can keep reacting like it did in the first step of propagation, to keep adding these bromines to the carbon skeleton. So this would be the two propagation steps. And then finally we have termination. So termination is the last thing. And that's when our sources of radicals come together, preventing any more propagation from happening. So you can draw a mixture of different termination events, but I'm just going to draw the most obvious. So if I just had two bromine radicals come together like this, the result is a bromine, and now we have no more radicals left. So no radicals to continue propagating. Okay, so all your radical mechanisms are going to follow initiation, propagation, and termination, and bromination just is more regioselective than chlorination. Okay, so if we were to predict the products for these, it's fitting to just say something like this. that we have both enantiomers here, and we have two enantiomers because a radical intermediate has the same electron geometry as those carbocations, meaning that they're sp2 hybridized. And when that bromine source comes and attacks that sp2 center, it's be able to attack that unhybridized p orbital from the front face or the back face, and that's where we get both enantiomers. But keep in mind this is regioselective, so that's why we're placing it on the secondary benzylic position. Chlorination is not regioselective, so we would expect a mixture of products. So if I had to predict the products of these, I would say that that would be one of them. I would say this is a product. I would say another one. Okay, and I would also say, I think there's one more. Okay, so these are all of my possible products that I would get. So notice how there's 1, 2, 3, 4, 5 major stereoisomers here, and with bromination we only got 2 major stereoisomers that were racemic. Okay, so that should pretty much sum up free radical halogenation. Okay, so the next reaction is a free radical addition of HBr to alkenes. So I did kind of want to bring back this point. If I took that same starting material and I subjected it to HBr, that was like the first reaction we learned in organic chemistry, where that pi bond acted as a nucleophile, grabbed that proton, and formed the bromine anion. Okay, so the results of that would have been, this tertiary carbocation. We generated that source of bromine, and then the next mechanistic step was that bromine anion coming and attacking that carbon skeleton, and more specifically at the carbocation, to show Markovnikov addition of that bromine to that pi bond. So addition of that bromine to the more substituted position. Now, in the presence of peroxides, and more specifically peroxide radicals, we're going to observe anti-Markovnikov addition. Okay, so let's just kind of go over that mechanism. Okay, so let's look at this specific example. So you see that we have this, peroxy source over here. So peroxides are 2 oxygens single bonded to each other. So something like this. We typically see hydrogen peroxide, which looks like this, H2O2, or something like this. Okay, so peroxides just have this oxygen-oxygen single bond that has a relatively weak bond dissociation enthalpy, so it's relatively easy to, cleave that bond and, generate peroxide radicals. Okay, so let's just show that mechanistic step. So we have this peroxy compound over here, and we're subjecting it to light so that we should expect, homolytic cleavage of that bond to observe 2 peroxide radicals. Okay, so that peroxide radical is going to, react with HBr. So we can just say we have something like this, HBr, to generate tert-butanol, so the alcohol version, and we generated that bromine radical. Okay, so what happens now is when that bromine radical comes into contact with the carbon skeleton, there's something that's pretty important here to note. So when this carbon bond breaks, so we're seeing that one of those electrons is coming into contact with that bromine, we're going to generate a radical on the more substituted position. So this is that regioselective point. So basically what happens is we added the bromine to the less substituted side because we wanted to form that radical on the carbon skeleton on the more substituted side. Okay, so that, is pretty characteristic of what we've seen so far. And then we can take another equivalent of HBr, and we can see breakage of that bond to isolate our product. Okay, and this would be, our product that we just generated, and this is, a stereocenter at that carbon. But don't forget that we did generate that bromine radical again, so it's important to realize that there is potential to constantly add to this, carbon skeleton. So we would expect a termination event okay, and we we can see that we have our initiation, our propagation, and our termination event. So whenever we see HBr in the presence of peroxides, we would expect anti-Markovnikov addition of that bromine to that pi bond, so the less substituted side. And don't forget, you are racemic at that position. Okay, so finally, the last thing we have is allylic bromination. And although you don't need to know the mechanism for this class, it does follow the same initiation, propagation, and termination steps. So our reagent of choice here is the NBS reagent. So it stands for N-bromosuccinimide, and I drew it down here. Okay, and this nitrogen-bromine bond has a relatively weak bond dissociation enthalpy, so it is a source of bromine. So I guess the key reactive point, or the key mechanistic point, is that we're going through a allylic radical. So the allylic position is one carbon removed from the carbon-carbon double bond. So it would be this position. So this is the allylic radical. And there's one key reactive point that you have to consider whenever you have allylic radicals, is that they can resonate. So we need to check for alternate resonance structures where maybe that pi bond is becoming more stable. So if I showed this sort of resonance, and I can draw the other major contributor, or the other resonance structure, we would see that this is the result of resonance. So, in this first structure, we had a monosubstituted alkene, so monosub-alkene. And we also noted that we had a tertiary radical. So over here, we have a tri-substituted alkene, but we have a primary radical. So it looks like we have conflicting information. So we have this monosubstituted alkene, which is less stable than a tri-substituted alkene. And then we have a tertiary radical, which is more stable than a primary radical. So which one wins? And it's always radical stability, it's always alkene stability that wins in this argument. So the more substituted the alkene is, the more stable that product is. So although we have a less stable radical in this structure, we're still going to go through this intermediate because of an increased stability of that alkene. So then we can, assume that a source of bromine radical is going to come and attack that primary radical. And if I had to predict the products, it would be something that looked like this. Okay. And the minor product would be the results of that monosubstituted alkene. Okay. And that's it. That's pretty much all there is for Chapter 8. So make sure you practice these funky mechanisms and you'll be golden.